Hey everybody, it's Ripley back again. Oh, we're in the thick of it now. We're going to talk about something called parametrics today. And this is a new way what's the right word? To think about the way a function can be defined. Now, hopefully you remember a little bit. I know they're tricky to keep on the hard drive, but you remember polar coordinates. Remember how polar equations and polar coordinates redefined how we thought about functions, and that was really useful, especially when we wanted to talk about a function that didn't pass the vertical line test. Remember, we made roses and we made limaçons and the mesquites and all those good things. Parametrics does that as well. Now, let me show you kind of how this works. Let's say you've got an ant that's marching across a coffee table. All right, it's do-do-do-do-do. It starts here and it cruises around looking for food and it does this. Okay. Now, clearly this isn't a function. This is going to be really hard to define in terms of a function. We'd have to do it piecewise, right? We'd have to like carve out all these little spots where we break the vertical line test and then have to turn this thing into one of these, which would be god awful. Doesn't work. Might be tricky to define it as a polar coordinate, or excuse me, as a polar equation as well, right? I mean, you got all these weird angles and it doesn't have these perfectly smooth curves. Plus, we don't know. The ant may have stopped. Whoops. The ant may have stopped right here and hung out for a while, right? And that's really tricky because theta doesn't stay stagnant, and there's no way to really tell what's going on with the ant when it stops, as it were. So what we have is we have a system called parametric equations. Now, let me show you how this works. What it says is this. Okay, let's say that our ant started here at t equals 0. Let's say that it finished here, and I'm just going to pick an arbitrary number. Let's say this is 20 seconds later. All right, and let's say that this value right here is going to be, I don't know, t equals 3, and this is going to be t equals 15. Okay? Now, notice it's still on a plane. It's on the coffee table. And this plane has points x, y. But what we do in parametrics, rather than describe one variable as being a function of another, what we do, I need something obnoxious, is we say, well, screw it. Since we can't define one variable as a function of another easily, what we're going to do is we'll just define each variable as a function of time. So this point right here would correspond to x of 0 and y of 0. So now instead of one function, one independent variable, one dependent variable, we have one independent variable, which is t, that's called the parameter, and two dependent variables, x and y. All right, so this is x of 3, and this is y of 3, etc., etc., and I could fill that in for all of these points. So t is called, oh, I'm lagging a little bit today, is called the parameter. Parameter. All right, and that is the most obnoxious color ever, isn't it? Let's go back to black. Now, let me explain what we're doing. We're simply adding another structure, which we're calling t, and forcing x and y to be a function of that. Okay? So instead of having a function like f of x like we had here, what we're going to have is we're going to have a set of two functions, x of t and y of t. And hopefully those big brains of yours are cranking and saying, wait a second, if we can do this for 2 space, why can't we do it for 3 space or 4 space or n space? Bingo! You got it. All right, parameterization is uber powerful. All right, because we're not confined to this whole, I got to pass the vertical line test, and this is an x, and this is a y, otherwise I can't write it as a function. I mean, simple things like equations like x equals y squared can be a pain in the butt to wrap our brains around because it doesn't pass the vertical line test. And this may describe the motion of something, right? And we have to go, wait, I have to turn this into y equals x squared, and then I have to think about it. No. Maybe we can kill off a couple of things at once. For example, let me do that one. Watch. If I let y equal t, and I let x equal t squared, do you agree that if y is t and x is t squared, then this turns into the rectangular equation y squared equals x, right? because x equals t squared and y equals t. So there's nothing to it. So this is a parametric way to write this rectangular way. So this is parametric, this is param, and this is rectangular. Rectangle. Boy, it does not like those, does it? Rectangular. All right? That's kind of interesting. Let's take a gander real quick at what that looks like on a calculator. I'm going to walk you through some steps here because you're going to use your calculator here. What's going on with my computer all of a sudden? Oh, that's scary. I don't care. All right, so what we're going to do is, let's make this thing bigger. You're going to go to your mode, and you're going to toggle down until you get to parametric. See where it says function. Now, we've done this before. This is not your first rodeo. Remember, we had polar before. Well, now we're going to do parametric. And hit enter. All right, and then we're going to go y equals. And I'm going to let, what did I say? X of t equals t squared. Notice that it auto-fills that t squared in. And y of t equals t. Now, let's look at the window. Remember how we always kind of want to look at the window and see how this works. Like back in polar, remember the default settings were that theta was between 0 and 2 pi. Let's see what we got here if I look at my window. Whoa, check it out. Now, whoa, that kind of did a whole bunch of things all at once, didn't it? This has my T-min of 0 and my T-max of 6.28. This is very, very similar to what happened with polar. Oh, I'm going to hiccup. Pardon me. Now, the problem is for whatever reason, they set these defaults from 0 to 2 pi, when really, if we think about it, time doesn't necessarily have to start at 0. In fact, if it doesn't, for example, what if I set it at 0 equals -10? Watch what happens. Hey, look, it built the other side. That's kind of cool, huh? See how that worked? And it carved this guy out. Now, that is a really simple way to understand what parameterization can do, how we can take a simple equation like this and turn it into this guy really quickly. And it's not a function in the rectangular sense of being a function where y equals f of x, etc. Now, we'll get into more complicated ones, I promise. I'm also going to show you how to do things like circles and ellipses and hyperbolas and all kinds of good stuff like that. Now, remember, this window is going to cause you guys some fits. So you got to make sure, when in doubt, if you want to start t at 0, which realistically makes sense, but theoretically, there's no reason we can't start it at a different value. Okay? All right, so let me shrink this sucker back down and open this guy back up. All right, so let's think about this. What would something like, I don't know, how about, let's try and take a rectangular equation and write it as a parametric. That's always the easiest. Watch this. If I go, let's go y equals 3x minus 4. Okay? There's that guy. Now, how do you think, we know what this looks like, right? It looks like this. I go down to -4. I've got a slope of +3, and it's going to look something like that, right? Now, I'm going to come up here because I'm going to have to do a little bit of work. So I'm going to let x of t, watch how simple this is. I love converting x of t and y of t. I'm going to let x of t equal t, and I'm going to let y of t equal 3t minus 4. Now, if I want to get the whole line, then I have to define t, between -infinity and infinity. Do you see why? Because watch. Let's just set up a little deal here. I'm going to set up instead of a coordinate tree, I guess this is like a coordinate shrub. I'm going to go x and y. Watch what happens. When t equals 0, x is 0, and y is -4. When t equals 1, x is 1, and y is -1. When t equals 2, x is 2, and y is 2. Let's do one more. I know you guys, it's just killing you guys, but I like to do that. When t equals 3, x is 3, and y is what, 5? Now, you see what's going on here? What we're doing with this tree is we're only picking up this point, and then this point, and then this point, and then this point right here. So we're only carving out this side of the line, and I'll show you that here in just a sec. So let's hop over to our handy-dandy graphing calculator and see what we got here. Watch this. Pow! It's like a cooking show. It's already done for us. X was t, y was 3t minus 4, and here's our graph right here. See how that works? I've only got half. I changed my window from 0. Again, I could go from 0 to 10 if I wanted to, but I chose to go from 0 to 2 pi. So just like we thought, if I want the whole line, then I'm going to want to go from like negative 10, and watch what happens when I hit enter. Booyah. Gives me the whole line. See how that works? So you really do. You got to be careful about what you're looking at. You're going to want to marry what you're looking at on the screen with this window, because every now and then you'll get misinformation. Remember that craziness that happened around the t-step? If t-step changes, now it's not so bad on a line, but I'll show you what happens with a circle or with an ellipse or something like that. Okay? You got to be careful with that. We saw that with polar. If this t-step gets too big, this is the distance that the calculator calculates each value for. So you'll end up with, instead of having a smooth curve, you'll end up with this clunky, boxy looking thing. All right, let's get back to it. Now, so that's simple. Given any function f of x, I don't care how ghastly it is, I don't know why this thing changed to blue. Given any function f of x, I don't know if I want to call it x squared minus sine of x plus 3. If I want to turn it into a parametric, if it's already a function, simple. I just let x of t equal t, and I let y of t equal the square root of t squared minus sine of t, what did I say, plus 3? Man, nothing to it. Now, what about the other way around? What if I had, for example, I don't know, let's say that x of t equaled 3t plus 1, and y of t equaled the tangent of, say, t plus 2. All right? Let's take a look at what this function looks like first. So what I say, 3t plus 1 and tangent of t plus 2. I don't even, to be honest with you, I don't even know what that thing looks like. This is too big. I want it small. It doesn't matter. So back to here, and I'm going to go, what I say, this was 3t plus 1, and then this guy is going to be, whoops, enter, and what I say, tangent of t, I gotta look again, you guys, sorry, my brain's not all there, t plus 2, so I'm gonna go t plus, oh, look at that, 2, and in paren. Wow, look at that. Huh, so think about what's going on here. What do we have? We have a tangent. It appears, let's take a gander at my window. My window's still from negative. If I wanted to, I could say, since it's tangent, I could go negative 2 pi, and hit enter, which is negative 6.28. So look at that. Wow. It appears as though, since we know that this is 2 pi long, it appears that we had a horizontal stretch, right? No doubt about it. And then we had a horizontal shift. Well, let's see if we can wrap our brain around why that happened and make some sense of it. Ooh, I can move this over just a little bit. Ooh, I like that. So let's go over to this. So why is that? Well, here we go. See if we can figure it out. Now, remember, y equals f of x. I'm going to write that right in here. Y equals f of x. But I could also think of this as y as a function of x, right? They basically mean the same thing, since y always equals f. So really, if you think about it, couldn't I just go, I'm going to solve for t in this equation as a function of x? It's kind of like the whole inverse operator that we did back in Algebra 2. Do you agree that if x of t equals 3t plus 1 with a simple puff of algebra, t equals x minus 1 divided by 3? True?